and then we'll move on into rotation, which we're really just starting in the class. All right, so again, two types of problems. We have these impulse problems, and that just says that F is equal to delta P over delta T, which is M delta V over delta T. Remember, this is just Newton's second law. This is our acceleration right here, M times A. And then we have conservation problems. Conservation problems just say that P initial is equal to P final, remembering that these are vector quantities. That is to say, let's say I have two particles. You can have more than two, you could have three, you could have a billion particles, but we'll just deal with two particles on the test. So you'd say M1 V1 initial plus M2 V2 initial equals M1 V1 final, M2 V2 final. All right, so that's sort of like the dodgeball problem that we worked. Within collisions, you can have a couple different kinds. You can have elastic collisions. Elastic collisions, field forces are involved. Sorry. Field forces are involved in these because field forces are conservative forces. They conserve energy and they conserve momentum. All collisions conserve momentum, all right, but only a certain class of collisions conserve energy, and those are elastic collisions. And then you also have inelastic collisions, and these are only conserve momentum. These are every other type of collision. So a car running into something, people running into one another, whatever. All other collisions except for those that conserve energy are inelastic. Really, the only good example of elastic collision are gas particles colliding. Anytime you have field forces that are involved. And when gas particles collide, they don't actually touch, right? They're just repelled by the electric charges. Um, okay, so that's it for chapter 5. You have a certain class of problems for impulse, which we'll work right now, and then a certain class of problems for conservation of momentum. So let's look at both of those. And the good news is all problems are different, but the way you work these problems is largely the same. All right. You'll have the equation sheet for this upcoming test that'll have these various formulae. Though we still don't have that many just yet. It is, yeah. Mhm. And it's on the web too if you want to look at it there. So let's look at this number 5 here. This is fall 07. Um, so on the test, it's laid out in the order that we cover it. So the first part of the test will be energy, the second part of the test will be momentum, and then the third part of the test will be rotation. So this would be a momentum problem. When you get into the momentum section, if you see something about force, then you'll know that it's going to be one of these impulse problems where I'm going to have to use this idea that F is equal to delta P over delta T. I know that because it's asking for a force. Anytime it's a conservation of momentum problem, there aren't going to be any forces involved. We won't really talk about the forces at all. And so when I do this, I need to figure out how is that momentum changing. Now, as you look back through the old test, you'll see some different types of problems. I'll ask you, like, what is the force involved? What is the change in momentum? Or maybe what is the final velocity after this force has been acting? In this one, I'm just asking for the force. So I need to figure out what is the change in momentum. This is the change in momentum. In some problems, I ask explicitly for the change in momentum. And the change in momentum is m times Vf minus Vi. All right, divided by my time. So this is the change in momentum. And in this case, it's going to be the mass, which is 80 kilograms. Um, be careful in this because sometimes in problems you'll have extra information that you don't need. So for example, like if I gave the mass of Superman was 100 kilograms, you wouldn't use that. It's not necessary because the thing that's changing velocity here is Lois, right? Lois is falling, Superman zooms along and he catches her, right? Taking her from a velocity of 50 meters per second to 0 seconds, or to 0 meters per second in 0.1 seconds. So Lois is the one who's changing velocity, and so Lois's mass is what we need to consider. So be careful. Sometimes you give extra information, and that's just sort of par for the course, but make sure that you're looking at the body that's actually changing its momentum. And in this case, Superman is the one exerting the force, but he's exerting the force on Lois, and we know that because it's Lois that's actually changing her speed. Okay, so I have my final velocity here as 0 meters per second, minus my initial velocity, which is 50 meters per second, and then divide that by my time, which is 0.1 seconds. See, 80 times 50 is 4,000, excuse me, divided by 0.1, so 40,000 newtons is the answer. That's one class of problems, and I think you have one problem like that where I ask you what is the change in momentum, or rather, not what is the change in momentum, what is the force, or I could ask you what is the change in momentum, or after this force acts, what is the final velocity, those sorts of questions. Okay? That's how you work it. Yeah, it would kill her, right? That's the point, that if she goes from being 50 meters per second to 0 in that amount of time, it's not good for Lois. Okay, let's go on the movies then. All right, now the other class of problem are like these. These are conservation of momentum problems, like number 4 here. Again, this is Follow 7 Exam 3. Um, in these conservation of momentum problems, you're always going to have two bodies at work. And in this case, I have me, I'm holding a gun that's 10 kilograms, and then I'm firing a 10-gram bullet, and I want to know what is the magnitude of the velocity of you and the gun. So this is me. I'm holding, you get the idea. I'm holding a gun. All right, inside the gun there's a bullet, and it's getting ready to go. Initially, my momentum is equal to 0 because nothing's moving. And then I fire the gun. So there's me. I'm just going to draw it as a cylinder. There's my gun, and my bullet is traveling with a velocity of 300 meters per second. So this has a velocity equal to 300 meters per second, and it has a mass equal to 10 grams, which is 0.01, is that right? Yeah, 0.01 kilograms. Don't worry, you don't have to do any conversions on this test for this particular part. Now you'll see when we get to rotation, you will have to do conversions for that. Okay? So I know also over here that my final momentum has to equal 0. Yeah. No, I know that the initial momentum is 0 because nothing's moving. Technically, we have three bodies here, although we're going to treat this guy as one complete body of 100 kilograms. So we only have two bodies. We have the bullet, and then we have me holding the rifle. Okay? And here, nobody's moving. And that's how I know that the momentum is 0. We had a similar question on the concept test. Remember when Amy and Gwen, they were sitting on the lake, and initially they weren't moving, and then they pushed off with one another. One of them went away at one velocity, and one of them went away at another velocity. It's a similar problem here. Uh, this bullet goes away at 300 meters per second at 0.01 with a mass of 0.01 kilograms. So this guy, who has a total mass of 100 kilograms, is going to go backwards with a certain velocity. And that's what the problem is asking. What is the magnitude of the velocity of you and the gun? So I know that the mass here is 100 kilograms. Again, that's you plus the 10 kilogram gun that you're holding. We had a similar problem in the concept test was a cannon that shot a cannonball. Same problem here. So there's not really a whole lot of variety in the problems on these. So once you see 3 or 4 of them, you've basically seen them all. Okay? So what I do is I say that my initial momentum equals my final momentum, 0 is my initial momentum. My final momentum now is going to be the mass of the bullet times the velocity of the bullet plus the mass of the guy times the velocity of the guy. And I'm looking for this, the guy plus the gun, actually. So I say 0 equals 0.01 times 300 plus 100 times v of the guy plus the gun. And then I solve that. So 0.01 times 300, that's 3. It's going to be what, 0.03. So I solve that for VG and I get 0.03 meters per second. So when that gun kicks back on you, it would make you move back at 0.03 meters per second. Now you have friction and stuff that's keeping you in place, but if you were in a frictionless scenario, that's what would happen. Not necessarily. So like in that dodgeball problem, that one didn't have an initial momentum of 0. The dodgeball problem with the movie, did y'all see that? We do that problem all together? Yeah, so in that one, you had one body moving initially, and then you had one body moving in the final state. Okay? So with conservation momentum, you can have a couple different types of problems. You can have one like with a dodgeball where you just have one thing moving initially, and then one thing moving finally. You can have one like this where nothing's moving initially, the initial momentum is 0, and then they split off from one another. That's also like the Amy and Gwen problem where the two girls, they were pushing off. And then you can also just have, we did a problem like this in class where both of the particles are moving, they rebound, and you have to figure out the velocity of one of them. Okay? That's it for momentum. I mean, yeah. Let's see if there's one here. Can I take this away? Oh, and then you can also have an inelastic, a perfectly inelastic collision. That's where they stick together, right? I think those are pretty easy because you just add up the masses, and so the algebra is a lot easier. See, I don't think there's one on this one. Make sure that you go through all those concept test questions too about momentum and force acting on one object, force acting on another object, how does the momentum change? A lot of those come back to this F equals delta P over delta T. But go through those concept test questions on momentum and make sure that you understand the relationship between the force and the change in momentum. Okay? I think y'all are probably pretty sort of okay on those. Okay. Okay, let's look at a rebound problem. Well, I'm just going to work one, okay? I mean, I don't know where one is right off. I'll just make up one. So I would have two particles. They're moving towards one another. Say this is 1 kilogram. This is 2 kilograms. This one's moving at 3 meters per second. This one's moving at 4 meters per second. And then they bounce off of one another. After they collide, they go in opposite directions. And let's say this one travels at 8 meters per second. And I want to know, what does this one travel at? We worked one, this is like one of the first problems we worked. I would say the initial momentum of this scenario equals the final momentum here. So the initial momentum is m1v1i plus m2v2i. This is my initial momentum. M1 is 1 kilogram times 3 meters per second plus 2 kilograms, and this is sort of the sticking point where people will mess up, times what? Not 4, but what? Negative 4 meters per second. It is a vector quantity, so you have to include that negative. It's part of the direction. A lot of people will mess that up, and of course you'll have answers that have that as a positive, but they're wrong. Those are the wrong answers. So make sure that you get the sign right. It is a vector quantity, so it has to be included. And then the final momentum will equal the same thing, but I'm going to have here 1 kilogram times negative 8 meters per second, because it's going to the left, plus 4 kilograms times V final, VF2. Okay, so I have 3 minus 8, that's negative 5 is the initial momentum, And remember, momentum is kilogram meters per second. No fancy units for this, it's just the basic SI units. So negative 5 equals negative 8 plus 4 VF2. So VF2 equals 3/4 meters per second. Right? 8 minus 5 is 3. Divide by 4, 3/4. Okay? You're just going to have one-dimensional uh, conservation of momentum. Uh, it could be one of those several classes that I mentioned. One or more of the particles not moving in the beginning, one or more of the particles not moving at the end. Okay? One or two problems like that? Just need to understand the idea that momentum is conserved. Momentum is conserved in elastic or inelastic collisions. Both, right. Momentum is always conserved, only in elastic. And I always think of that because, like, elastic collisions are really bouncy, right? They're really bouncy, and so those conserve energy better. EE, there you go. Rhea? Oh, yeah, you're right. I'm sorry. It should be, yes, yes. I'm sorry. You're right. I'm wrong. This should be 2 kilograms, 2, 2. Thank you. All right. They should dock my paycheck. Like when I get an answer wrong, just ding. A little counter up here. Okay. Yeah, no, I wouldn't want that. But we do that to y'all, so I don't understand. Like, we got a double standard going here, right? I get a mistake, and it's like, oh, sorry. You get a mistake. I'm like, oh. Okay. All right. Now, David, you're gonna have two-dimensional problems. I'm not gonna work them here, but you'll have you'll have one particle that comes in this direction and one particle that comes in this direction. They work out the same way, except that you say px initial is equal to px final, py initial is equal to py final, and so you get two sets of equations. Um, I don't know if we've worked one of these like this yet in class. We'll do it tomorrow. But y'all, the rest of y'all, you won't see a 2D problem. Yeah. Okay, but if you're pre-med, you might see it on the MCAT. Right. Okay. You have to find the x and y components of the velocity. And so like px initial would be m1 v1 initial x component plus m2 v2 initial x components. You have a cosine theta, sine theta terms for the x and the y components. Remember x components cosine theta, y components sine theta. Okay? But they work out the same way. It's just the algebra is a little more complicated. All right. Yeah. So am I. They have a, there were they only have 2 chapters on their test, but they have a lot more stuff on it. It's getting a little more complicated for them. Yeah. Okay. Um, rotation. And David, you're welcome to hang around, but y'all aren't gonna have a rotation on your test. We are gonna do rotation, but not till next week. Okay, so with rotation, you're gonna have some kinematics problems. Kinematics, so those equations that we dealt with, remember we had those equations V equals V naught plus AT, and X equals V naught T plus 1/2 AT squared. You're going to see those again, except we're not going to do any two-dimensional stuff because we're rotating. So there's no equivalent to projectile motion, all that business. So they're a little simpler than we had before. Except the equations don't look like this. Where we have V, now we're going to have omega. These are all Greek letters. This is omega. Yeah. And where we have X, now we're going to have theta. And where we have A for acceleration, now we're going to have alpha. So our equations are going to look like this. We'll have omega equals omega naught plus alpha t, and theta equals theta. Oh, well, we don't really do the theta naught. We'll just leave that off. Equals omega naught t plus 1/2 alpha t squared. But they work a lot the same way in using these. When you read through the problem, you have to figure out, okay, what is my initial velocity? What is my acceleration? What is the time? What is the position? So these are all just measurements of the velocity, the position, and the acceleration. And they work exactly the same way as they did in Chapter 2. When, yeah, I mean like over here? There are a few little differences. Uh, so I think it'd be better just work through some problems. Can we do that? Okay. Let's see. Okay, so here's one, number 14. It says in 1.2 seconds. Oh, wait, there's one more thing. Let me show you that here before we do that. We can relate these problems in this way. For all of them, V is equal to omega times R. X is equal to theta times R. And alpha is equal to omega, no, not omega, I'm sorry. A, acceleration, is equal to alpha times R. Think about the units here. This is in radians per second. This is in radians. This is in radians per second squared. So if I want to get to units of meters per second squared, I would multiply radians per second squared times meters. Radians isn't really a real unit, so we just sort of write it here as a placeholder. But it is a measure of an angle, right? An angle that in our angular position. So when I multiply this times the position, it gives me a linear quantity. So these are all related to one another by the radius of your path. These equations are all in your equation sheet. All of these, everything on this sheet. No, I don't know why I use Greek letters. Because of the radians? No. Right. Okay. Okay, folks. Let's try a problem. Sure. Yeah, you will have to do that. You will have to convert between the different systems of measuring angle. So we have three things to measure angles in: radians, degrees, and revolutions. In a circle, in a full circle, there are 2 pi radians, there are 360 degrees, and of course, that's 1 revolution. So those are our conversion factors. So for example, if I wanted to convert 45 degrees to radians, I would say, well, in 360 degrees, there are 2 pi radians. Y'all know what 45 degrees is in radians? Come on, y'all know this. Do your unit circle. It's pi over 4, right. So it's useful to know your unit circle just for life, I think. So this is 0, this is pi over 2, this is pi, this is 3 pi over 2, and then I come back to 2 pi. So it could be useful to know your unit circle for the test too. I mean, you don't have to know it. You can do it the hard way, but it's a lot better if you just know your unit circle. 0, pi over 2, pi, 3 pi over 2, 2 pi, 0, 90, 180, 270, 360. Remember, when we're talking about angular displacement, that counterclockwise is positive, but if we go clockwise, that's negative. And that's just because that's the way we do it. Okay? Right. Yeah, we're not going to have torques on this test. It's chapter 8. Yeah. Okay. Um, so let's try this problem now, because all of these things sort of come into play in this particular problem. I have a time of 1.2 seconds. That's t. I accelerate from rest to 12 meters per second. So careful here. This is my velocity. This is v naught. This is v final. The reason I know it's velocity and not angular velocity is why? Because it's not radians, right? Because the units here are meters. It says the radius of the car's tire is 0.5 meters. What is the angular acceleration? What is alpha in revolutions per second squared? Okay, so yeah, so here um, I'm going to have to first find, well, I know that omega equals omega naught plus alpha t. And I also know that v is equal to omega times r. So since I know v up here, I can find omega because I also know r. So omega then is equal to v divided by r. That's 12 meters per second divided by my radius, which is 0.5 meters. That's going to be 24 radians per second. Anytime you do a calculation like this, I recommend that you just convert everything back to radians, because radians is the SI unit. And notice here, like I didn't do any conversions or whatever, but whenever I'm relating V and omega, the units are in radians. Okay, so when I use this up here to find alpha, the angular acceleration, it's going to come out in radians per second squared. But notice, and it's sort of bolded and italicized, that I want it in revolutions per square second. Revolutions per second squared. So you have to convert it right. So that's 24 radians per second. And now I come up here and I say 24 radians per second equals 0 plus alpha, and t was 1.2 seconds. And then I find that alpha is 24 over 1.2. That's equal to 20 radians per second squared. But be careful, right, because it's right there, but that's not the answer. Because I want it in revolutions per second squared. So now I have to do one final thing. Radians per second squared. In one revolution, there are how many radians? There are 2 pi radians. So it's 20 over 6-ish. So C is the right answer. This is equal to 3 revolutions per second squared. I said 20 divided by 2 pi. But 2 pi is basically 6. It's 6.28 or whatever. Okay. Yeah, that's 2 pi. Okay. Right. Yeah. Once you get the hang of it that x is now theta, v is now omega, a is now alpha, uh, then these become a little more familiar to you. And if you look at the equation sheet for this chapter, where is it? Where is it? Oh, there it is. Okay. Yeah, so if you look at the equation sheet, uh, if you forget which is which, just look at the equations, and you know, this is my displacement equation. And then you can say, well, that equation looks like the one I had before. So now x is theta, v is omega, a is alpha. Yeah, right here, you mean? Yeah. Yeah, you could do that too. But there you go. Yeah, but I have s instead of x. Because usually s is used to define arc. Okay. There is one final thing, and that's centripetal force in this. Uh, y'all saw centripetal force in the lab when you did the little ball experiment. Y'all like that lab? We have the ball, it goes around in a circle. in the computer lab. Oh yeah, tomorrow. Yep, I have tomorrow. Yeah, y'all doing it tomorrow. I like that, man. All right. Clear this out. So that's you'll have kinematics, and in class, and if we're not in the online, but in class, uh, tomorrow. Yeah, we just sort of got into this. So, uh-huh. Yep. Yep. This is a smaller part of the test, and I've tried to understand that we've only had a few days on this chapter, by making the questions more, I don't know, more not hard. Can you say not hard? I'm trying not to say simple, straightforward, obvious. I'm trying not to use those words. So, yeah, so not hard. I like that. Not complicated. Okay, so centripetal force is a force that causes circular motion. It's really not a particular force, it's just a type of force. A type of force that causes circular motion. I never understood what centripetal forces were, until I came to realize that a centripetal force isn't really a particular force, it's a role that a force plays, right? So we have all sorts of forces, right? We have frictional forces, we have like tension and strings, you have like contact forces when you push on something. Any one of those forces can be a centripetal force if it causes circular motion. So for example, if I have, a ball on a string or whatever, if I swing this around, I'm causing this pin to move in a circular path. And so I have a force that's acting on it that's a centripetal force. It's the tension in the string. This tension in the string is the centripetal force. Or if I have a car that's moving on a path, this car is moving in a circular path. The centripetal force is what? The force on the car, but what's actually keeping the car on the road? The tires or the frictional force. So in this case, the force that's causing the centripetal force is the static friction between the tires and the road. So a centripetal force can be any type of force, but it's really the role that it plays that causes the object to move in a circular path, causes circular motion. Right, and this centripetal force, which I'll call Fc, sometimes you might see it as Fr. Sometimes I use those interchangeably. C for centripetal, R for radial, because the centripetal force is always towards the center of the circle. Radial, that's what radial means, always towards the center of the circle, along the radius. All right, so the centripetal force is equal to mv squared over r. And let me write that down also. The centripetal force is always towards the center of the circle. Always towards the center of the circle. And the centripetal force, the magnitude of it is this. So for example, here, my static frictional force, and my static frictional force is equal to mu times force normal, but it's also equal to mv squared over r. Why do you need a centripetal force? So an object with constant velocity, constant magnitude of the velocity, that's what this means. The vector with the two absolute values, the absolute value bars, it means the magnitude. So it has a constant speed in a circular path is always changing direction. It's always changing direction. It's moving in a circle, right? And so the direction is always changing. If I draw a picture, say of an object that's moving around in the circular path, the direction over here of the velocity is right there. Over at this point, the velocity is there. It's always tangent to the circle. So the velocity of our, even though the magnitude is the same, it's always 2 meters per second or whatever, the direction is always changing. That means you have to have a force that's causing this object to move in this way. And so this object also has an acceleration. That acceleration, we call it AC or AR, is equal to V squared over R. The magnitude of that acceleration is V squared over R. Okay, so those are the basic ideas behind centripetal acceleration. Let's work a problem. Any questions about this? We'll see this tomorrow in class. All right, let's look at this. A centrifuge is used to separate the red blood cells from plasma. I think you had a homework problem like this. Um, I would look at your homework closely for both of these chapters, or all three, 5, 6, and 7. The centrifuge is used to separate red blood cells from plasma. The radius of the rotation is 10 centimeters, so R is 0.1 meters, and the rate of rotation is 100 revolutions per second. In a given sample, the mass of the red blood cells is 2 times 10 to the minus 16, so that's M. And I want to know what force is required to separate the red blood cells from the plasma. So this force is the centripetal force, or it acts as a centripetal force. These blood cells are zooming around in a circle, right? They're in your centrifuge. They have the centripetal force which is acting upon them. So the force that's acting on them is that mv squared over r. But I have to do some hoops. I have to jump through some hoops to get this data into the right units. Because notice here, I have not v, right? This is a measure of what? It's 100 revolutions per second. Is omega. It's omega. So yeah, so our angular velocity is 100 revolutions per second. I'm going to go ahead and convert this into radians per second. There's a lot of unit conversions on this. There aren't as many on your test. So that's 200 pi. I'll just leave it 200 pi. Okay, so that's my angular speed. Now, what you can do here is you can say, well, V is equal to omega times R. That's my relationship that combines V and omega. And so V then is 200 pi times R, which is 0.1, or 20 pi. So that's V. I know M, and I know R. Now I can find my force. My mass is 2 times 10 to the minus 16. My V is 20 pi, which is what? 62.8 squared, divided by the radius, which is 0.1. And then you find that force. What is the answer? Looks like it has to be A. Is that right? I think that's right. That doesn't look right. No, it's B. 8 times 10 to the minus 12, yeah. Yeah. All right. So let's see, that's follow 7, that's exam 3. That's a good problem. You'll have potentially have something like that. 8 times 10 to the minus 12. So there were a lot of steps in this problem where you had to do sort of conversions, and you'll want to let your units guide you on that. Make sure that you convert everything to radians per second. Although you will find on some of the problems, more so next chapter, but like on the kinematics problems, that sometimes you don't really have to change the units. And with practice, you'll figure out when that is. Or if you just want to be safe, always go to SI units. And what are the SI units for angular displacement? Radians, degrees, or revolutions? Which is it? Radians. Always radians. So if you're ever in doubt, convert to radians. Okay? Let's do some of these others just for practice. Uh, let's see, you'll have one like this. Hopefully this will be a gimme. How many revolutions is 400 degrees? Well, you can just look at this, right, and tell me which is it. It's B, right? Because I know that one full revolution is 360 degrees, so it's going to be pretty darn close to 1. And there, B is really the only one that's possible. Hopefully that's a gimme problem. Um, let's try this kinematics problem here. If you will, we haven't done this one, right? 15. This is a good test. Fall 07. A dentist drill starts at rest and undergoes an angular acceleration. Gosh, what is angular acceleration? What's the letter for it? The Greek letter? Alpha, right. Alpha is like the Greek A, right? So if that helps you remember. So alpha is 10, t is 3 seconds, and I want to know the angle. That's theta, that's what we normally use. I also know that it starts at rest, that's omega. So theta, I'm looking for theta, that's omega naught times t plus 1/2 alpha t squared. This is actually omega naught. It's initially at rest. So this first term goes away. 1/2 of alpha, which is 10, times 3 seconds squared. 5 times 9 is 45. So C is the right answer. Rounding off to 1/6. So you will have likely a not complicated not a multi-step problem where it's really just sort of knowing what the values are, knowing what the right equation is, plugging them in. And then you could have a more complicated one like number 16 where you have several steps and you have to change units and just sort of be very careful as you go through, be very deliberate looking at the units. We did 14 already. Okay, let's try this one. This is another centripetal force problem. I have a car that's going around a curve. It says it's a flat road. That'll be important for just a second. This is the coefficient of static friction, and this is the radius of the curve. And I want to know what is the maximum safe speed at which the car can round the curve. You have a homework problem like this, and they come up on tests pretty frequently, so I guarantee you have a problem like this, but you'll have one that's very similar to it. Not necessarily a car problem, but a problem where you're doing a similar procedure. Okay, so let's see. I know that I have a force that's causing this car to stay on the road. Because if this force wasn't there, what would you do in the car? If you didn't have that force holding you on the road, you'd do what? Right, you'd just run off in the ditch, right? That's what you do when the road's really slick. If you didn't have this frictional force that's holding you on the road, this is Fs, you would just continue going off in a straight line into the swamp or the bayou or whatever. Okay? So I have that frictional force that keeps me on the road. And I know that that frictional force, Fs, is equal to, or is, my centripetal force, Fc. I know that Fs is mu times the normal force. The normal force is equal to the weight. I know that it's equal to the weight because it's a flat road. You won't see any inclined planes or banked curves on this test, so no more inclined planes till the final. And then m, yay, v squared over r. And then I want to ask myself, what am I looking for? Well, I'm looking for the maximum safe speed. This is how they calculate the speed for curves. Notice that the m's cancel. That's good because the maximum safe speed, the speed they put on those signs, is good for your VW Bug as well as your Dodge Ram pickup truck. We've really gotten into Punch Buggy. You ever play Punch Buggy? Like my whole family, like we're always looking for Volkswagen Bugs now. Punch buggy, punch buggy, punch buggy. It's like who can get the first one. We hit pretty light, except for my son. Like he really wails on his sister, huh? Oh yeah, yeah. All right, so let's see. I'm looking for the maximum safe speed, so I solve this for v. It's equal to the square root of mu g r. So square root of point 0.7, 10 times r, which is 50, point 0.7 times 500, so 3 square root of 350. I think it's c. Should be c. Yeah, 19. Okay. You see variations of this problem if you look back at the old test, but I would master it. Okay. That's sort of it for rotation. Let's look back and through some of the problems. You have any questions? We're going to see this again in class tomorrow and Monday, um, but it's good to get a little head start on it. Not getting past 18 there. Hmm? Yeah, there were a lot of it. That's why it was a good. This was a good test, man. I should just print this one out and give it to y'all. Okay, that's all. Unless y'all have more questions, I think we'll wrap up there. Any more questions though? Huh? Mm-hmm. I'm sorry. This is it's more for one-on-one students. All right. We'll have another help session on Tuesday at 2. Uh, Right. We're doing springs and energy. Uh-huh. I'll see if I can do 3. I've talked to my wife. I usually go home at 3 on Tuesdays. Yeah. Well, I think you have to ask yourself what's more important, physics or biology? No, don't ask yourself that. Don't tell anybody I said that.